In the universe's grand tapestry, woven from the threads of fundamental forces, the strong force stands out as the master weaver. This force is the glue that binds the universe's smallest constituents, holding together the very essence of matter. To understand this force is to unlock the secrets of the atom's core. Our journey into the heart of matter begins with the atom, once thought to be indivisible. We now know that atoms are comprised of even smaller particles, protons and neutrons residing in the nucleus, orbited by electrons. This is where the strong force takes center stage. It is the force responsible for holding the protons and neutrons together within the incredibly dense confines of the atomic nucleus. But what is the strong force and how does it work? The answer lies in a theory of exquisite beauty and profound implications, quantum chromodynamics or QCD. This theory, a cornerstone of modern physics, unveils the hidden world of quarks and gluons, the fundamental particles that interact via the strong force. Just as electromagnetism governs the interactions of electrically charged particles through the exchange of photons, QCD describes the strong force as an interaction between particles carrying color charge. Like the vibrant hues on an artist's palette, this color charge dictates how quarks and gluons bind together to form the protons and neutrons that make up our world. To delve into the world of QCD is to enter a realm where colors dance and interact in ways that defy our everyday intuition. Unlike the familiar colors of our visible spectrum, the colors in QCD are abstract properties that dictate the strong force interactions. Quarks, the fundamental building blocks of protons and neutrons, come in three colors: red, green, and blue. These colors, however, have no relation to the colors we perceive with our eyes. They are merely labels, representing different quantum states that quarks can occupy. Just as electrically charged particles interact by exchanging photons, quarks interact by exchanging gluons. These gluons, like their photon counterparts, are the force carriers of QCD. However, there's a crucial difference. Gluons themselves carry color charge. This remarkable property has profound consequences for the behavior of the strong force. Imagine a game where colored balls are constantly exchanged. Each time a ball is thrown and caught, the colors of the players change according to the color of the ball. This constant exchange and color-changing game is a simplified analogy for how gluons mediate the strong force between quarks. Quarks, the fundamental particles that make up protons and neutrons, are as elusive as they are essential. They come in 6 different flavors: up, down, charm, strange, top, and bottom. Each flavor possesses unique properties like mass and electric charge. However, what truly sets quarks apart is their color charge. This charge governs their interactions via the strong force, binding them together within protons and neutrons. The strong force dictates that quarks can only exist in combinations where the total color charge is white or neutral. This color neutrality requirement leads to the formation of composite particles like protons and neutrons. A proton, for example, consists of 2 up quarks and 1 down quark, with their color charges combining to create a white or color-neutral particle. Gluons, the force carriers of QCD, play a crucial role in maintaining this color neutrality. As gluons are exchanged between quarks, they ensure that the total color charge within a bound system like a proton remains neutral. This intricate dance of quarks and gluons, bound by the strong force and governed by the rules of color charge, forms the very foundation of matter as we know it. Section 4. Confinement, the mystery of hidden quarks. One of the most intriguing aspects of quantum chromodynamics, or QCD, is the concept of confinement. This principle states that quarks are forever trapped within composite particles like protons and neutrons. They can never be observed in isolation. Imagine trying to separate 2 quarks within a proton. As you pull them apart, the force between them doesn't weaken like gravity or electromagnetism. Instead, the force remains incredibly strong, like an unbreakable spring. This immense force arises from the self-interacting nature of gluons. As you try to separate quarks, the gluons that mediate the force between them form a narrow tube or flux tube of strong force energy. The further you pull, the more energy is stored in this flux tube. Eventually, the energy in the flux tube becomes so great that it's more energetically favorable to create a new quark-antiquark pair from the vacuum. These new quarks then combine with the original quarks, forming new mesons. Therefore, instead of isolating a single quark, you end up with more composite particles. This phenomenon, known as confinement, explains why we never observe free quarks in nature. they are forever bound within the confines of composite particles, their individual identities hidden from direct observation. Section 5. Asymptotic freedom, the dance of quarks. Asymptotic freedom, a groundbreaking concept in QCD, describes how the strong force behaves at extremely short distances. Unlike other fundamental forces that weaken with distance, the strong force actually weakens as quarks get closer together. Imagine two quarks bound within a proton. At large distances, the strong force acts like a powerful spring, keeping them confined. However, as the quarks get closer, the force between them weakens. This weakening occurs because the gluons that mediate the strong force begin to interact more strongly with each other, effectively screening the color charge of the quarks. This phenomenon of asymptotic freedom has profound implications for understanding the behavior of matter at extremely high energies. At these energies, quarks and gluons behave as if they are almost free particles, no longer feeling the powerful confining force that binds them within protons and neutrons. This state of matter, known as quark-gluon plasma, is thought to have existed in the first few microseconds after the Big Bang. Recreating these extreme conditions in particle accelerators allows physicists to study the fundamental properties of the strong force and gain insights into the early universe. Section 6. QCD's triumphs and unresolved mysteries. Quantum chromodynamics stands as a triumph of theoretical physics, providing a robust framework for understanding the strong force and the structure of matter. Its predictions have been repeatedly confirmed in high-energy particle collisions, solidifying its place as a cornerstone of the standard model of particle physics. The discovery of the charm, bottom and top quarks, predicted by QCD, showcased the theory's predictive power. Furthermore, experiments at particle accelerators have provided compelling evidence for the existence of gluons and the phenomenon of asymptotic freedom. Despite its successes, QCD still presents physicists with profound questions. Understanding the precise mechanism of confinement remains a major challenge. The theory also faces difficulties in describing the low-energy behavior of the strong force, where quarks are tightly bound within protons and neutrons. Moreover, QCD's integration with the other fundamental forces, particularly gravity, remains an open question at the forefront of theoretical physics. Unifying these forces into a single, elegant framework is a grand challenge that continues to drive research in areas like string theory and quantum gravity. As we continue to explore the subatomic realm, QCD serves as both a guidepost and a source of inspiration. Its elegance and complexity remind us of the intricate beauty that underlies the universe's most fundamental laws. Unraveling the remaining mysteries of QCD holds the key to unlocking a deeper understanding of the universe's building blocks and the forces that govern their interactions.